Hey there, math physics students. Mr. Simon here. This video is going to be doing some of the free body diagrams that we did not get time to do before Thanksgiving. It's not that these problems were that much more difficult. We just didn't want to go over Thanksgiving break, then come back and do a test. That would not be good for you. And obviously we have to save a little bit of time since we're only meeting 50 minutes twice a week instead of the normal every other day for an hour and a half. So we kind of skipped over these. But I'm going to go through number 3, number 4, and number 5 on page 62 and 63 in your book. We're doing the free body diagrams. So we did on page 61, number 1. We did number 2 on page 62. And we did a couple that were in the homework section. But we didn't get to 3, 4, and 5. I'm actually going to do number 3 last because it's probably, I don't even know, probably, it is more difficult, we think, than number 4 and number 5. So we're actually going to go to number 4 first. Number 4 is known in the engineering and physics world as an Atwood machine problem. Atwood machine is really anytime you have two masses connected together by a string, rope, or something like that, strung over a pulley. So it's one system. However fast one is going to go, that's how fast the other one's going to go. And there's only two things given to us for an Atwood machine problem: the mass of each object. So I got the mass of the cube and the mass of the cylinder. What's different about this is we have two objects. So what do I do with free body diagrams? Do I have to draw 1, 2? Doesn't matter if I draw A or B. Since we don't know at this point, I'm going to start by doing letter A. So I'm going to draw a free body diagram with letter A. Remember that a free body diagram is a simple sketch showing all the forces acting on an object. So you just draw a box maybe the size of one of your fingernails. So that's A right there. The first force we can draw on every single free body diagram is the weight, or the force of gravity. We can find the weight by using that little equation, W equals mg. So I take my mass of 4.7 kilograms times 9.8 meters per second squared, and I get a weight of, I think it's 46. I'm going to double check this. So I got 4.7 times 9.8. You get 46.06. Well, close enough we can call that 46 newtons. So that's how hard gravity is pulling it down. Again, the force of gravity is synonymous with weight. I've got a rope attached to the top of letter A. Ropes can obviously exert forces, and we call the force in a rope the tension. Simply T for tension. And here's the interesting thing about ropes. I don't know if it's interesting, but there are a couple of rules about ropes. One rule is the tension stays the same throughout the whole rope. So if I have any rope, any string, anything like that, whatever the tension is in one spot of the rope, that's the same as the tension in another spot of the rope. Even if something that's my keychain, if I push on it and it's got a certain tension here, it's got the same tension everywhere. The other thing about ropes is they can only pull. You can't push with a rope. Try to attach a rope to something and push, it just doesn't work. So if I've got a rope attached to the top, the rope has to pull away from the top where it's attached. And again, the force in a rope we simply call the tension. Those are the only forces acting on A. There's no normal force, there's no support force, it's not sitting on a table or floor, it's just hanging loosely there. So I've got just two forces, gravity pulling it down, tension pulling it up. Now which way is A going to go? Well, I can reason, since A is more massive than B, that A is going to be going down and B is going to be going up. Because the more massive one has to win. And I like to draw my acceleration vectors right on the free body diagrams, as those who have me in class know. So right next to A, I'm going to remind myself that this one's accelerating down. It's the more massive one. So right below that, I'm going to use Newton's second law. I'm going to net up my forces in the y direction to see how that mass accelerates. So I'd like to write a couple subscripts there. Net, which means the summation or totaling up of the force, and I only care about the y forces. Now there aren't any x forces, but if there were, I wouldn't care about them. Newton's second law says acceleration happens in the direction of motion, and the force has to happen in this direction of acceleration. So I'm just totaling up the forces in the y direction. Now it's going down, and weight is going down. So weight is actually a positive force. It's going in the same direction that we're moving. But tension is going in the opposite direction. And if you remember earlier this year, opposite direction simply means negative. Or negative means opposite direction. So my weight is a positive force because it's in the direction we're moving. Tension is a negative force. It's in the opposite direction. Well, I know the weight is 46 newtons. I don't know the tension. In fact, I was asked to find the tension. I know the mass is 4.7 kilograms. And I don't know the acceleration. In fact, I was asked to find the acceleration. And at first glance, I might say, beans, nuts, shucks, I'm stuck. Because I have two unknowns. I can't solve right now. And if you give me the acceleration, I'll calculate the tension for you. If you give me the tension, I'll calculate the acceleration for you. But I don't have either one. So I'm stuck. Until I remember math class. I remember being taught if I have two unknowns, I'm going to need two equations to solve for those two unknowns. If I have three unknowns, I'm going to need three equations. If I have 17 unknowns, I'll need 17 equations. So since I have two unknowns, I got to find another equation. I got one equation right here. I got to find another one. Where am I going to find that? Free body diagram number 2. I got my other mass, B, that's moving up at the exact same acceleration rate that A is moving down because they're connected, it's a system. The first force I'm going to draw on every single free body diagram is a force of gravity or the weight. W equals mg. I got 3.2 times 9.8. And I get 31.36. You can just probably call that 31.4. I've got a rope attached to the top of B right there. Remember the rules of ropes, they can only pull. So it's attached to the top and it can only pull. And again, the force in the rope we call the tension. Another rule of rope says the tension has to stay the same throughout the whole rope. So whatever the tension is on A, it's the same tension on B. Those are the only forces acting on B. So I'm going to net up my forces in the y direction to see how that mass is going to accelerate. Now B is moving up at the same rate A is moving down, but B is moving up. So notice that tension is in the proper direction that it's moving, and weight is in the opposite direction that it's moving. So my tension is my positive force, my weight is my negative force. Well, I don't know the tension. The weight is 31.4 newtons. I know the mass is 3.2 kilograms. And I don't know the acceleration. And for just a moment in time, I might say, beans, shucks, I got two unknowns again. But now I realize I have two unknowns, but I have two equations. And if I have two unknowns and two equations, I can solve. Now, if you forget how to do this, there's a couple different methods. One is called substitution. I can take one of these equations and rearrange it for, say, t. So t equals blah, blah, blah. Take blah, 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 stick it in for t, substitute, get rid of t, and I can solve the acceleration. Or I can take one of the equations and solve for a. A equals yada, yada, yada. Take yada, 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 stick it in for a, substitute it out, and solve for t. And those will work just fine and get you the correct answers, no problem. But for Atwood machine problems, there's an even easier way. I'm going to line these two equations up right underneath each other with the newtons matching up, the tensions matching up, etc. So it's going to look like this. I'm going to take my pink equation, 46 newtons minus T equals 4.7 kilograms times A. And right underneath that, I'm going to write my blue equation. But I'm going to line up all the proper things, meaning I'm going to line up my negative 31.4 newtons under those newtons, the positive T under that T, the kilograms and acceleration underneath each other. Again, substitution will work. This is even quicker. I'm going to line the two up. I'm going to add them together, which gives me a positive 46 minus a 31.4 for a total of 14.6 newtons. Here's the beauty of lining them up. The tensions will always cancel. You also have a positive T and a negative T. Goodbye, Mr. T. Over here, sometimes students think, well, I'm going to add those together and get a squared or 2a. No. If you have 5x and you add 3x to 5x, you just get 8x. So 4.7x plus 3.2x simply gives me 7.9x. But instead of x, of course, we're using a for acceleration. It's not 2a, it's not a squared, just 5x plus 3x is 8x. So now I divide my 14.6 by my 7.9, and I get 1.85 for my acceleration. Boom, just like that. Easy peasy. Now I have to solve for the tension too, but to solve for the tension, all I need to do is substitute that value in to one of the previous equations. So I can substitute that back into this equation, or I can substitute into that equation. You're going to get the same answer regardless. Doesn't matter which one you choose. So I've got 1.85 times 3.2, and I'm going to add 31.4 from the other side, and I get a tension of 37.3 newtons. And I promise you, if you stick it into this equation, you'll get the same tension. Might be a couple decimal places off because of rounding here or there, but you're going to get the same tension. That's an Atwood machine problem. Students actually do pretty well on these. In a typical year where we don't have COVID and we have a typical test, easily 90% of the students get 90% of the points on a problem like this, if not even better. Because for Atwood machine problems, once you've seen one, you've seen them all. There's nothing else we can change. Think about it. You're just given the masses of each one. There's no friction, there's no this, that, nobody else pushing or pulling. So the only way we can change one of these is to change the mass of one of those. Maybe this is 7 kilograms and that's 12.9 kilograms. That's it. Other than that, it flows the same way. And that's why students have very few problems with these. We easily would have done this if we'd had a normal non-COVID class year. On the next page, number 5 is very, very similar. There's one slight difference. This some teachers refer to as a tabletop problem. Some teachers still refer to it as an Atwood machine problem because you still have two masses connected by a string over a pulley. I think of it as an Atwood machine problem. The only thing that's really different is this one's going to move up and down. That one's going to move horizontally. So we have one moving in the y direction, one moving in the x direction. Now students will sometimes ask, well, which way is it going to go? Well, think. If I've got a tabletop and I've got a mass on it, I've got over the end of the pulley a mass, and I let that go, if that starts going up, you got to come find me because I got to see that. There ain't no way that baby's going up. If I let that system go, that's going to go down and that's going to be pulled to the right. It's possible that there's too much friction and you let it go and it doesn't move at all. But that, nothing to do there. But I sure as heck, if I let that go, and there's no way that baby starts floating up in the air. That's not the physics world we live in. So I know that one's got to go down. Similar to the last problem, two objects, I'm going to draw two free body diagrams. Doesn't matter which one I draw first. Me personally, I like to draw the hanging mass first. That's just me. So I like to go to that hanging mass. And go, again, the first force I can draw on every single free body diagram is a force of gravity, otherwise known as the weight. W equals mg. So we've got 4 is on the end of the string. 4 times 9.8 should give me 39.2 newtons. If I can do my math correctly in my head, 39.2 newtons. There's no normal force, there's no tabletop, no floor, it's just hanging there. But there is a string on the top side. Remember that ropes and strings can only pull. And the force in a string of rope we call the tension. That free body diagram looks just like the ones for number 4, because it is just like the ones for number 4. I'm going to net up the forces in the y direction to see how that mass is going to accelerate. There aren't any x forces, but if there were, I wouldn't care about them. This one we said has got to be accelerating down. Again, I like to put that acceleration vector right by my free body diagram. So if it's going down, weight is in that proper direction. So weight is positive. Tension is in the opposite direction, so tension is negative. I know my weight is 39.2 newtons. I don't know the tension. In fact, I was asked to find the tension. My mass is 4 kilograms, and I don't know the acceleration. In fact, I was asked to find the acceleration. For just a moment in time, I might say, beans, I'm stuck again. But then I realize I'm going to be okay. I'm stuck at first because there's 2 unknowns, but I know of 2 unknowns. I'm going to use 2 equations, and I know where I'm going to get that second equation from, that second free body diagram. So there's one equation with 2 unknowns. I'm going to go to that baby right now. Let's go with orange. All right. So here I've got this mass. Again, the first force I can draw on every single free body diagram is the force of gravity or the weight. W equals mg. 6 times 9.8 should be 58.8. If I'm doing my math correctly in my head. Now this one is on a tabletop. So it is being supported. There's a support force, technically known as the normal force, holding it up. So gravity's trying to yank it down, but the tabletop's holding it up. And those 2 forces are going to cancel each other out. By the way, it's not Newton's third law canceling each other out. Newton's third law is if object A puts a force on object B, then object B puts the same force back on object A. It's not Newton's third law. They're just 2 forces that cancel each other out. I've got a rope attached to the right side, and ropes can only pull, and the force in a rope we call the tension. I analyze and realize that this one has to be accelerating to the right, can't be going to the left. If it's moving to the right, friction is going to act to the left. And since it is on a tabletop, as opposed to just being suspended in air, there's going to be some friction between the tabletop. And I know that friction force is equal to the coefficient of friction, that little decimal represented by the Greek letter mu, times the normal force. That's that little equation for friction force. So I take the coefficient of friction, 0.42, times my normal force of 58.8, and I get 24.697. We'll call it 24.7. There's my free body diagram for the tabletop problem. What's different is this is moving in the x direction, not the y direction. So when I total out my forces, F net in the x direction, we only analyze the forces that are affecting the actual acceleration. It's part of Newton's second law. So it's moving horizontally in the x direction. I only care about the horizontal x forces. I don't care about the y forces anymore. Since it's moving to the right, notice that tension is in the direction it's moving. And friction is in the opposite direction it's moving. So tension is positive, friction is negative. So it's not W minus T, and that one's T minus W like Atwood's machine. That might be W minus T just like Atwood's machine, but this is not T minus W. It's moving in the X direction. I only care about the X forces. Weight is not an X force. So I've got T minus 24.7 newtons equals 6 kilograms times A. And at first glance, I might say, beans, I got two unknowns again. But now I realize, hey, no worries, I now have two equations. And I can use that substitution method again, or I can line them both up like I did in the last problem. So once we get this far, it's just like the last problem. So I'm going to line the two up again. 39.2 newtons minus T equals 4 kilograms times A. And right underneath that, a negative 24.7 newtons and a positive T equals 6 kilograms times A. I'm going to line those babies up and add them together. So I got a 39.2 minus a 24.7. I get 14.5. My T's are going to cancel just like the Atwood machine problem we just did. Got a positive T, a negative T. Goodbye, Mr. T. Again, don't worry about 2a, a squared. No, 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 no. 4x plus 6x is 10x. If you got 4 apples and they give you 6 more apples, you just got 10 apples, man. You don't have 10 times 2 apples. You don't have 10 apples squared. You just got 10 apples. That's all you got. Divide both sides by 10. A is 1.45 meters per second squared. Very similar to the last problem. The only difference is this. We're netting up in the X direction for that baby. Just like the last problem, substitute into either one of those other equations. Either one is fine. I'm going to do the orange equation. So I got 1.45 times 6. And I'm going to add 24.7 to both sides. And I get 33.4 newtons. And I guarantee you that if you stick that acceleration into the green equation, you're going to get the same tension. Might be slightly off from rounding, but you get 33 point something. Again, just like the previous problem, students do pretty well on this on a typical test when we don't have this COVID crap going on. We do a couple of these in problem class, we practice them a little bit, and 90% of the students get 90% of the points on these. Number 6, I'm not going to do. If I do that, I'll do it on a separate video. We don't always get to an inclined plane in honors physics or math physics our junior year. We sometimes do. But I do want to go back now and do number 3. Number 3 is actually more difficult than number 4 and number 5. There's only one free body diagram. We're only pulling it with one force. But what's different about this is the angle. The angle. That baby right there. And angles screw people up. So I'm going to try to explain this as best I can. Hopefully it won't screw you up too bad. But the angle changes one very important thing, as you will see. All right, so we're pulling our wagon. But we're pulling at an angle. When we're pulling at an angle, things change. But I'll start with a regular free body diagram. There's my wagon. First force you can draw on every single free body diagram is the weight, the force of gravity. W equals mg. I take the mass, 30 kilograms, times 9.8. Get 294 newtons. Normally, the next thing we do is draw the normal force right back up. Can't do that now. Anytime I have an angle, before I draw the normal force, I say, easy, big fella. Don't draw that normal force yet. Angle changes things. I was kind of telling myself that. So I'm going to just put the normal force on hold. That support force from the ground. We'll come back to that in a second. I'm pulling with a force, this is the force of U, of 200 newtons, but I'm doing it at an angle of 30 degrees. And that changes things. I'm going to assume I'm accelerating this to the right. You know me, I like to put my acceleration vectors right on there, because that's the way I'm pulling, right? So friction must be acting to the left. Friction is mu times the normal force. I have mu 0.45, but I don't know the normal force yet. Here's what's different about this. We like to net up the forces in the x direction and y direction, if that's the direction things are moving. This thing is moving in the x direction, but I'm not pulling at the x direction. It's not moving at the 30-degree angle direction. I pull my angle, it's still moving in the x direction. So I've got to take this vector and divide it into its two components. The components of vectors in Unit 2. So I'm going to divide this into its two components. In my classes, I talk about going to grandma's house to eat some apple pie. And if you drive your car, you got to drive due north, south, east, and west. But our Uncle Charlie flies a helicopter, he can go straight there. So him going straight there in a helicopter is equivalent to us driving our car, taking a left turn and going that way. So I've got to divide my helicopter vector into my two roads. I simply call this the x component, and I call that the y component. With a little trigonometry, sine and cosine, I can find those values. That's equal to the sine of 30 degrees times the hypotenuse of 200 newtons. Make sure you calculate this in the degree mode. Sine of 30 degrees is 0.5, right? So that's just going to be 100 newtons. That's the opposite side. The adjacent side, I'm going to use the cosine of 30 degrees times the hypotenuse. So I got the cosine of 30 times 200 gives me 173.2. So again, a little reminder of vectors. If Uncle Charlie flew his helicopter to grandma's house and traveled 200 miles, in our car we traveled 173.2 miles, then took a Louis and traveled another 100 miles. Here's where the normal force is different. Normally, like in these problems, I just had two forces in the y direction, weight and normal force. And this thing is moving sideways, so I know it's the up and down forces have to cancel. If it's not moving up and down, the total up and down forces have to cancel. They're equal and opposite. Here's moving horizontally, so my up and down forces have to cancel, but now I have three up and down forces. I have weight, I have F sub y, and I have my normal force. So my normal force is going to be, in this case, smaller than my weight. The rule of thumb is not normal force and weight have to cancel. The rule of thumb is up and down have to cancel if it's moving horizontally. Well, I now have two up vectors and one down vector. So that's going to be 294 minus 100 for a total of 194 newtons from my normal force. So again, the rule of thumb is not up and down, is not normal force and weight have to cancel if it's moving horizontally. The rule is if it's moving horizontally, up and down have to cancel. Often, there's only two, so they're equal and opposite. At an angle, there's three. Uno, dos, tres. So my two up have to cancel out my one down. That changes the normal force, which now changes the friction force. So now I take my 0.45 times my normal force, which is not 294, it's 194. That gives me 87.3 newtons. And that's a kind of confusing thing. And this is a typical mistake people make in the test, is they'll just make normal force and weight the same. Well, when you make normal force the same, that changes your friction force, and that changes the whole answer. But we would only take 1 or 2 points off for that in a typical test. I got all my forces solved for. I'm going to net up the forces in the x direction, because it's only moving in the x direction, the horizontal direction. I don't care about the y direction. I don't care about the 30-degree direction. I only care about the direction this baby is accelerating. Of all those vectors, only 2 of them are x vectors. The x component of your pull force, which means you're pulling with 200 newtons, but only 173.2 is actually used to actually move that thing sideways. Those are the only 2 x forces, and it's only moving in the x direction. So I got 173.2 newtons minus 87.3 newtons equals the mass of 30 kilograms times the acceleration, which gives me 2.86 for my acceleration. Again, these are a little bit more difficult, at least history has shown me as a teacher, than 4 and 5. And it's all because of that angle and that normal force thing. So these are some of the normal free body diagrams we would have gotten to in a normal non-COVID school year. Hopefully this makes some sense to you. If you're thinking about going into engineering or more physics, you kind of want to know these. And if you take advanced physics next year, we do these all over again, and we'll make sure that we review these. So other than that, it's just good old physics, good stuff to get to know. So I enjoyed spending the last half hour with you. Hopefully this made sense to you. You can always check with me if you have any questions. So, all right, have a good day. As always, lots of love for you guys. Hang in there. We're going to be fine. We're going to get through this whole COVID thing. All right, have a good day.